Hi everyone, welcome to the Black Hole Information Paradox mini course, lecture 2. Suvrat, please take the conference. Thank you.
Thank you very much, Jesse. Thank you everyone for coming for this second lecture. As Jesse requested, I thought I would start just by giving you some references, which is what I was in the process of doing. So in fact, much of the material I'm discussing is covered in this review called Lessons from the Information Paradox. So this is the archive number. There's a published version in PhysRep, in Physics Reports, which you can read, but the archive one is fine. It's identical. And in fact, if you look at that archive version, it'll give you more references to look at. So this, I would say, is the main reference for most of what we'll say. I'll say, this reference is a few years old. I'll say some things that are a little newer, but a lot of the material we are covering is covered here. There's another shorter perspective article which is useful to look at, which is called Failure of the Split Property. And that one is 2110.05470. Okay. We also, so these are two overarching references. I'll try and give more specific references as we go along. In terms of what we were discussing last time, the reference I wanted to give was by a paper by Candelas, and let me just give you the reference now. Wow. This is only a reference for some of the material we covered last time about propagation of waves, vacuum polarization in virtual spacetime. Spacetime. And this is PhysRev D. This is 1980. Okay. There was also some material I discussed which just had to do with the classical nature of the Schwarzschild solution, and that material you will find in standard GR textbooks. But as I said, this one is the main review, and everything I said, in fact, you can also find here. You'll also find this reference in this review. Yeah. Okay, so that's what I wanted to say about references. Maybe before I start the main, and as we go along, I'll give you some more specific references as and when we make note of them. But once again, many of the references will already be here. So before we go on, I wanted to stop and check if there are questions from last time. And if there are questions, I can take them now, and then we can go on. If there are no questions, that worries me a little bit because, some of this material I'm sure is new to at least some of you. So, if you think about it, I'm sure you'll have some questions. Yeah, okay, I see there's one question. Go on, yeah.
Hi, can you hear me?
Yeah.
So my question is that last time the discussion was when you said, like you described the equation of a scalar field near the horizon. And the idea was that at near horizon limit, all the angular degrees of freedom goes away. But why can we be so sure that there are no non-perturbative effects in these cases?
Yeah, no, we can't be so sure that there are no non-perturbative effects. This is a, it's a perturbative calculation. In fact, I'll explain maybe later in this lecture to what extent we can expect corrections to this calculation. It's not only non-perturbative, there are already perturbative corrections to this calculation. And I'll explain what the parameter is. The parameter is usually 1 over S, where S is the black hole entropy. And you'll find there are perturbative corrections to this calculation already. So I'll say a little bit more about that. So just to be clear, it's not the case. We are not claiming that this calculation is something that's exact Rather, we are claiming that, this is a leading order calculation. Maybe it could get corrected in perturbation theory and so on, but we'll discuss some of those corrections later in this lecture. So it was not being claimed that that calculation is exact. It is not exact. We know the right answer is that calculation is corrected, and it's certainly corrected non-perturbatively.
Yeah, maybe I will put the camera. So the question that I have is related to the previous question. I asked you last question. I didn't understand the whole picture. It is about the radiation. How I understand that the radiation. In fact, my question was about more about how I understand that the radiation is indeed from the interior of the black hole. Because when we computed, we took into account only field outside the horizon, phi. But how I really believe, how do I really understand that this is in fact a radiation that comes from the inside of the black hole?
Yeah.
And because of that, the black hole evaporates. That's what's my question.
It's not important that the radiation should come from inside of the black hole for the black hole to evaporate. You see, if the radiation, you're right, that the calculation we did was purely done outside the black hole. However, you see, if you're an observer who's far away and you see the radiation emerging, then you see just by conservation of energy, you know that the energy inside is going to reduce. So, imagine you're sitting at some sphere which is 10 times the black hole radius. Right? For you, what you see is some radiation emerging. It doesn't matter to you whether the radiation is coming from inside or whether it's coming from outside, or even 0.1 times the radius outside and so on. That is not important for you. You consider the whole thing a subsystem, and that subsystem is losing energy. And precise, the fact that question of whether it's coming from inside the horizon or outside the horizon is not important. In fact, you're right. The calculation we did was mostly outside the horizon. So you could say even that the radiation is emerging from slightly outside the horizon. Yeah? But that doesn't prevent the black hole from evaporating, right? Because if you're an observer who's far away, it's clear that that radiation will carry away energy, and therefore it must be the case that the black hole must evaporate.
Okay.
So it's not important for the black hole to evaporate to argue that the radiation is coming from inside.
Correct.
When you burn a gas, you have a gas flame. It's not important to say that the flame is inside the gas, right? If the flame is burning, then you know that the gas must be reducing in the cylinder. Right? It doesn't matter if the gas has come out and it's burning, or if it's inside and it's burning. As long as there's a fire and there's a source of energy, which is the gas, it must be reducing.
Okay, I understand the idea. Thank you.
Okay. Yeah, go on. I think a question from Harpreet. Yeah. Harpreet has a question, right? You want to ask her? Does he need to be unmuted, or is he unmuted already? Or? Okay, I'll assume that I can see Harpreet Singh has his hand raised, but maybe there's some audio problem, or you can type. Hi, Harpreet, can you hear? Can you ask your question? Your hand is raised. Okay, while you're waiting for that, could you again comment on the assumption on the distance? Harpreet, you're not audible. Not audible to me. And I guess not to anyone else, right? Jesse, can you hear? Can you?
No, I cannot hear him.
No, so you're not audible, Harpreet. Maybe you can type. Yeah, in the meantime, let me say something about the assumption and the distance. The assumption and the distance was, and this is something I want to emphasize a little bit more. It was that these points are just across the horizon. Okay, so, or actually just in front of the horizon, as we were just discussing. Okay, so x1 was here and x2 was here. Okay. And this distance was much smaller than RH, right? But much greater than M Planck and other such terms. Okay, so that's what this assumption was. So we were computing, we computed the 2-point function just outside the horizon, and then we transformed it and we got the form of the radiation. And in fact, I want to explain something more about this. But that was the assumption that we needed to make, because we used a form of the 2-point function that was that it was, the 2-point function in the UV. It wasn't affected by the curvature. It was the 2-point function in the regime where the geometry looks approximately flat. So that's why it has to be much, much smaller than our edge. But we didn't want to take care of, quantum gravity effects or anything like that. So it's much larger than M Planck. Okay. Are there any other questions? Okay. So if there are no more questions, I will go on to, there's one more question, Gustavo.
Yes, I've got a question. It's about if there are some fields, I mean, like electromagnetic potential, do we have to impose some boundary conditions on the horizon on these fields?
It was not completely audible to me, but the question I thought was, do you have to impose boundary conditions? This is not a question about specific fields. So I did the example for a scalar field, but in general, the same calculation will work for all kinds of fields, which have a mass that's below the temperature of the black hole. So if there are very heavy fields, then, those modes will not get excited. But as long as there are fields which, they might get excited, but they'll all eventually fall back into the black hole. They won't propagate out. But as long as, we are discussing some other fields, there's no problem in doing this calculation. We did not impose any boundary conditions at the horizon. I want to emphasize. We allowed both ingoing modes and outgoing modes. So sometimes when people solve the wave equation in this background, we assume that, we are imposing, you work in a setup where you're looking at quasi-normal modes, which are obtained by imposing infalling boundary conditions at the horizon. In fact, it's important for the study of Hawking radiation that we do not impose infalling boundary conditions. We allow both infalling and outgoing radiation, because Hawking radiation is outgoing radiation. So we don't impose any specific boundary conditions at the horizon is the short answer. Okay, question is, outgoing modes takes the form r to the 1 minus d by 2 apart e to the, that just comes from solving the wave equation, Harpreet. For instance, in 4 dimensions, it looks like the wave looks like e to the I k r by r. The fact that it looks like e to the I k r by r, that's the factor, d is 3, so it's 2 by 2. So that's the factor you're referring to, r to the 1 minus d by 2. That just comes from solving the wave equation at large r. So if you do it in other dimensions, you'll get this factor. Yeah. Okay, so let's proceed. If that addresses the questions. So I want to say just remind you what we did, and then say a little bit more in relation to one of the questions about the distance between the points, right? So the assumption, the result we arrived at last time was that if one looks at psi a omega L prime, okay, this side, this looks like delta L prime, okay, where this beta was 2 pi over kappa. And this is called the surface. This kappa was some term which is called the surface gravity. How were these modes A, omega L defined? These were defined by integrating phi with u to the I omega naught, where omega naught was related to omega by a factor of kappa that I explained last time, near u goes to 0. Okay, and this is u goes to 0. And so they were obtained basically by looking at this, looking at this very near horizon region and doing some, integrating it with some function of this kind, okay, which oscillates with some given frequency as u goes to 0. And it oscillates an infinite number of times because, if you think of u as log of small u, then small u goes to infinity as u goes to 0. If you think of u as e to the minus small log u. e to the minus log of small u. Okay. Then you see the small u goes to infinity as u goes to 0. And therefore, this mode, whatever it is, oscillates very rapidly. Okay, so it oscillates a lot as you go here. And that's why doing this integral in a small region is enough, and using the 2-point function in that small region is enough to completely work out this form. Okay? Now, you might ask the following question. You might say, okay, maybe I did that, but, the result that we wanted was the following, right? The result we wanted was the data here, right? Because what we really want to say is that the observer who's here sees some outgoing radiation out here. Why is it sufficient to look at what's happening in the very near horizon region? This is also related to the question that was just asked about these points being very close to the horizon. So knowing the 2-point function of the field in this very near horizon region, why is this sufficient to calculate the final state on Scri+? So this is a question that's a natural follow-up to the question about the distance between the points. The reason is to look at the geometry of the black hole collapse. You see, the way we draw Scri+ is a little deceptive, because in fact, this is u goes to infinity. Okay? So, Scri+ is measured by a null coordinate, which is small u, to be differentiated from capital U. Okay? And this small u is usually, defined as t minus r, where r is the radial coordinate in Minkowski space. In the small u, it's called the retarded time sometimes. In this retarded time, this region is u goes to infinity, and this region, which is the past boundary of Scri+, is u equal to minus infinity. Now, the key point is that if you look at some region here, this region is a semi-infinite interval. So let me just draw it with a different color. If you look at some region here, this region is a semi-infinite interval. Okay? So if you just trace rays, you will find that it's the physics that's very close to the horizon that determines this data in this semi-infinite interval. So provided you're looking at physics for a time much after the black hole has collapsed, then most of the data, in fact, comes from the data that's very close to the black hole horizon. Okay? So this aspect of the geometry is a very important aspect of the geometry. In fact, if you open Hawking's original paper and try to read Hawking's derivation for Hawking radiation, you will not find the calculation that I presented to you. Instead, you will find a calculation that tries to trace rays from Scri- as they bounce off the origin and go to Scri+. And the main physical point in this ray tracing calculation, and also here, although it's a little hidden here, is that the data on most of Scri+ is determined by what's happening to the very short distance physics near the horizon. Okay, so this was a little hidden in what we said. It was hidden because I said that we were looking at these modes that look like e to the I omega r at Scri+. And then I said, we could determine the state of the modes by looking at the very short distance behavior. And you could have legitimately asked me, saying, if you want to know the state of a field, you can't just look at the 2-point function in a very short region and determine the state of the field. And the reason you can do that here is because, of the way space gets blown up, in that a very small region right near the horizon gets blown up to a semi-infinite interval far away. And that's the reason that, knowing the short distance behavior near the horizon is enough to determine the final state of the fields for almost all of Scri+. Okay. So this is the point which I wanted to emphasize. It was in fact implicit in the equations we wrote last time, but I didn't say it as explicitly as I should have. I see.
Sorry, there was a question.
Yeah.
So the beta, the temperature factor, it is, I guess, if I'm not wrong, it's 2 pi over kappa, right? Or
yes.
Yeah, so the kappa was a coordinate dependent quantity, because I think we defined it as some FFR, or I'm missing something.
No, kappa is defined as f prime r by 2.
Okay, so
I think I defined it here. It's not coordinate dependent. It's it's part of the metric. I can write it again, but I think I defined it. Here. Yeah.
Right. So why is it not coordinate dependent? Because it depends on f prime at our edge over 2. Right.
Yeah,
Sorry, I think I missed that. Yeah. I thought like maybe one can choose a very clever coordinate system where the kappa goes to 0.
It's the horizon.
I'm,
yeah.
I'm sorry.
Okay. Okay. So is that clear to everyone? That's why. So that's the reason, by the way, this calculation we did of 2-point functions and looking at modes, you can do anywhere in flat space. You can just draw a null coordinate anywhere in flat space. And you can show there are modes on opposite sides of that null coordinate that are highly entangled with each other. That's in fact what happens when you take Minkowski vacuum and you break it up into 2 Rindler vacua. That doesn't tell you the fact that you have these that the state on one side is thermal. It just tells you that the state in that very small distance looks like it's entangled with the state on the other side, and therefore it's thermal. What's special about the black hole geometry is that that very small region near the black hole horizon gets blown up to the semi-infinite interval near Scri plus, and that's why you can predict the state in Scri plus by looking at that very small region. Okay, so that's an aspect of the geometry you should keep in mind. Okay, good. So now let me say a little bit more about what Hawking's paradox was. So what Hawking said, last time I said this in words, was he said, you look at this answer that we got, right? This answer. And he said, this answer looks like it's, sorry, I should have written a dagger here. This answer looks like it's consistent by saying that the density matrix of the system looks like 1 over z e to the minus sum of omega n omega, where n omega is this number operator, which is a omega dagger. I'm again not being careful about the measure. You should of course write an integral rather than a density matrix, rather than a sum and so on. But I'm not being careful about that. We can do that carefully, although it's not important for the physics of what follows. And you see, the reason this is, this seems very, very appealing is because this is the density matrix of some, this is the density matrix that would correspond to a set of decoupled simple harmonic oscillators, each with frequency omega, put in a thermal state at a temperature which was related to this beta, at an inverse temperature that was given by this beta. If you put the system in this kind of a thermal density matrix, then it's consistent that if you were to compute the expectation value of this number operator, then you would get the Boltzmann factor that you had previously. Okay, what we wrote previously was in fact the number operator plus 1. If you compute the expectation value of this guy, it looks like e to the minus beta omega by 1 minus e to the minus beta omega. So there's an extra factor of e to the minus beta omega. Okay, but the point is that either way, this is a Boltzmann factor, and it's precisely what you would get if you were to take a simple harmonic oscillator and put it in a finite temperature state. Okay? Now, the key point about this is that this is a mixed state, right? And Hawking's point was that, if you go back to the Penrose diagram that we were drawing, then you could start the system in a pure state. Okay. And this pure state corresponds to a density matrix to rho initial, which is just psi psi. Okay. Then unitary evolution cannot take psi psi to rho final, which is mixed, which is the one that we wrote last time. Okay. And the reason for that is that unitary evolution always takes rho in to something like U psi, psi U dagger. And this new rho n, I call this thing rho tilde n, also has the property that rho tilde n squared is equal to rho tilde n, which is a sign of the fact that the state is pure. And this guy also satisfies rho n squared is equal to rho n. But it's easy to check that if you look at this density matrix that Hawking postulated, or Hawking said is consistent with the correlators that Hawking computed, it doesn't satisfy rho squared is equal to rho. It's a mixed state density matrix. And in fact, a thermal density matrix never satisfies rho squared is equal to rho. Okay. So Hawking's point was that, if you compute the correlators that we computed, then, it looks like the density matrix you get is a thermal density matrix. And that's inconsistent with the fact that you expect that if you started with a pure state, you should have got a pure density matrix in the end. So today, in fact, this was something that was already asked, which was, how have we really kept track of corrections in Hawking's computation? So Hawking's computation, seems to be robust because it relies only on the very short distance behavior of the field. But have we really kept track of corrections even in that very short distance behavior of the field? And is Hawking's calculation accurate enough to determine, to really reach this conclusion that the final state is mixed? Okay, so that's the question that I want to ask and address today. So the question is Hawking's calculation precise enough to lead to a paradox? Okay, I want to take a bit of a detour before I do that. And I want to give you, some amount of material into statistical mechanics. And I want to ask a slightly different question. And then we'll come back to this question about, is Hawking's calculation precise enough? So the question I want to ask is, how close are pure states to mixed states? And you will see why this is related. It should be intuitively clear why this is related. It's related because, Hawking's calculation is saying that, look, the final state that we have is a mixed state, whereas a pure, we should have got a pure state. And so, it makes sense before we try and ask whether Hawking's calculation was precise enough to ask how close pure states could be with respect to mixed states. Yeah. Even if the final state was pure, how could Hawking radiation carry information about the interior of black hole? Yeah, we can address that issue a little later. If the final state was pure, how could it carry in? The first question is the final state pure? Okay. If the final state is just some random pure state which is not related by unitary evolution to the initial state, that would be a different kind of paradox. So for instance, you could say the final state is always the same state or something like that. So there's no unitary evolution between initial and final. Right now, we are just discussing Hawking's initial paradox. And his paradox was, that the final state looks like it's mixed. We will discuss by the end of this course the mechanism for how the radiation carries information about the initial state. But that's not what I'm going to discuss right now. Right now, I want to ask this question. I will address your question, but perhaps by the 4th or the 5th lecture. Yeah? Because that's a higher order question than the question of whether the final state is mixed or not. Yeah. Okay, so let me remind you, first, let me remind you that there are two ways we can have uncertainty in quantum mechanics. We say quantum mechanics is probabilistic, but there are two ways this can happen, right? So imagine you're shorting a cat state, right? You're shorting a cat. I'm not very good at drawing cats. This is my cat. This is alive. Okay. And then we can have a cat which is dead or sad, right? Maybe you can make it sad rather than dead. Okay, so this is one way we can have a cat which is, one way we can have uncertainty, right? So if you measure the system with probability A1 squared, cat is happy. Okay. Probability A2 squared, cat is sad. Okay. So this is, a Schrodinger cat state. right? Which says that cat is happy with probability A1 squared, cat is sad with probability A2 squared. However, even in quantum mechanics, we can have a slightly different way in which we can have the same kind of result for this particular question about the cat being happy or sad, and that is that we consider a probabilistic mixture of the state psi. So let me write happy state, and we assign a probability A1 squared, and the sad state, to which we assign a probability A2 squared. Now, this probabilistic mixture is different from the superposition that we have before. Okay? So the probabilistic mixture corresponds to a particular density matrix. Okay? Let me stop drawing cats now and let me write down what the density matrix would be. So let me call the state happy 1 and let me call the state sad 2. This guy corresponds to a density matrix, which you could write as A1 squared 1 1 plus A2 squared 2 2. Okay. And if I want to compare this density matrix with the state psi equal to, sorry, with the A1 1 plus A2 2, which corresponds to the density matrix, then these two density matrices are different. In terms of asking the single question of whether the cat is happy or whether it's sad, they give you the same probabilities. But there are other questions which will give you different answers. Okay? For instance, if you measure a general expectation value of some operator A, then in the mixed state, you would give you mod of A1 squared 1 A1 plus mod of A2 squared 2 A2. Whereas in the pure state, we would get interference terms would correspond to, first you would get these terms 1 A1, okay? And then you would also get this term, but you would also get mixed terms which correspond to plus A1 star A2 1 A2 and plus A2 star A1 2 A1. Okay. So these cross terms, there's some, if your observable A doesn't have any cross terms, then you can't differentiate between this pure state and this particular mixed state. But if your observable A does have cross terms, then for some other kinds of questions, you will get different answers in this pure state than in this mixed state. Okay. So there's a difference between, just saying that there's some uncertainty and saying that the system is in a mixed state. And that's something that we should be careful about. So what I want to ask today is about, in what sense are, these kinds of pure states different from these kinds of mixed states in a generic case. Okay. So this is, of course, a particular two-state system. Okay? And here you can see that, pure states look pretty different from mixed states, because provided I measure any observable which has, some cross terms, and most observables will have some cross terms, I can immediately see that a pure state is pretty different from a mixed state. Okay? And in fact, our intuition is often trained on these kinds of two-state systems, which tell us that, look, pure states are obviously different from mixed states because, look, pure states have these cross terms, and these kinds of mixed states, which maybe give you the same probabilities for some observables, are just obviously different when you measure some other observables. So it's very easy. It's, it all sometimes seems to us to differentiate pure states and mixed states. Okay? So I want to now explain to you how in a statistical setup, it's often very hard to differentiate pure states from mixed states when you have a very big system. Okay? So the question I want to ask, I'm going to now ask a similar question to the one that I asked now. Okay? So say we have a system and we consider some energy levels and we focus on about some energy E0 minus delta. Okay. Okay. So often in statistical mechanics, we consider the microcanonical density matrix. Okay. The microcanonical density matrix is the density matrix, which is this one. Okay. Where you just sum over, you just say you have some equal probability of having all of these states. And so you just sum over all of these states, but it's a probabilistic mixture of all of these states. What is this W? This W is the number of states and is often called E to the S. Okay, so this is how you define the density, the entropy in the microcanonical ensemble. Okay. So this is one notion of what kind of state you can have. This is the mixed state that I want to look at. Okay. Alternately, I can look at a pure state, which is some superposition of all of these guys. Okay, so I can look at a pure state and I runs over the same range. And so now I want to ask, and there's of course a pure density matrix. How close is this pure density matrix to this guy? Okay, that's the question that I want to ask. So before I ask this question, I need to explain to you what it means. Okay. What does close mean? And the second question I want to ask is, we want to examine typical states. Because you see, there's only one microcanonical density matrix here. It's the, this is the unique microcanonical density matrix. You just sum over all energy levels. But here, of course, there are many pure states. I could take one energy eigenstate, or I could take something else, and so on. And the question I want to ask here is, let's say I take a typical state, and you could tell me, what does typical mean? Okay. 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 So let me answer these two questions, and I'll tell you how you can get a rather clear answer to these two questions and how it has a bearing on the information paradox. Okay. Regardless of what this has to say about the information paradox, what I'm about to say is a pretty useful exercise in statistical mechanics that all of you should be aware of, because it's something that appears a lot when we study quantum information in the context of black holes. Okay. So let me answer the first question, which is about the meaning of close. Okay. So the first thing is, notice that, from the point of view of the density matrix, this density matrix, which is the mixed density matrix that I want to look at, is obviously different from this density matrix, right? So sometimes, in mathematics, you might say, let me look at trace of row 1, row 2. How close are they? Or define some measure which measures how close one matrix is to another matrix. And that's just obviously different. Right? These two density matrices are different. But we don't want that kind of a mathematical notion of closeness, which some mathematician would use if they had access to all the matrix elements of the density matrix. Okay. So we want a physical definition of closeness. Okay. So we want to ask, from the point of view of physical observations, how easy is it okay? So that's the notion of closeness that we want to look at, okay? Let's say we make a set of physical observations And we are an observer, we are making some observations. How easy is it for us to determine whether rho pure is the same as rho? Of course, if you give me everything about rho, you give me all the e to the s times e to the s matrix elements, then I can determine this difference. But that's not what we want to look at. We want to look at the simpler question, right? Which is how easy is it or how difficult is it if you're a physical observer who's making one measurement, okay, or 10 measurements, or some small number of measurements. Okay. So let me remind you. So let me first try and answer this question, right? So in quantum mechanics, observations always have to do with projectors. Okay, this is the other thing which it's quantum mechanics 101, but we shouldn't forget. And that's because what we can really measure in quantum mechanics are probabilities for various projectors. Okay, for instance, say I give you an observable O, which has some spectral decomposition that looks like this. And if I measure O, what I'm really going to measure, the information that I get, is information about these projectors pi. You might say, I also get information about these eigenvalues lambda I, but this information I can change just by normalizing O differently. And I could say, let me take O to 10O. If you do that, all of these eigenvalues go to 10 lambda I, but the probabilities that we have don't change. Okay? So the information that we have in quantum mechanics, doesn't have to do with how we scale observations or what units we use. These eigenvalues have to do with things like units that we use. But the information that we have in quantum mechanics has to do with the probabilities of various results. So it always has to do with the expectation values of projectors. The reason this is important, as I'm about to say, is that, the answer I'm about to give right now doesn't depend on normalization. It's not like, just by using an observable that's 1 million times the observable I was looking at, you can make pure states less close to mixed states or more close to mixed states. Okay, so the answer we are giving doesn't depend on how we normalize the observables. And that's because, in quantum mechanics, observations or information always has to do with probabilities of projectors, and we don't have a choice in how to normalize them. Probabilities are supposed to add up to 1. Okay? Okay, good. So let me make this more precise. So given a projector, we want to compare in a typical pure state and trace of rho p. This is rho and this is p. Okay, they're different even though they look the same, but they're different. Okay, so we want to compare how these two values differ. Okay, so this was my answer to my first question, right? What was close? So the answer to the question of what is close is, given a projector, which is P, we want to compare how close this value is to this value. Okay, this is the microcanonical density matrix, and this is a typical pure state. Okay, now I have to address the second question, which is, what's a typical pure state? Right? So you see, what is typical? Okay, so see, we can pick any state subject to normalizability. Okay. So the Hilbert space, in fact, is a copy of CP W minus 1. The reason for that is that, you can pick these complex numbers. There are W of these complex numbers. But, one state is the same as another state if I rescale it by a complex number. If I rescale the whole state by a complex number, I get, the same state back. And therefore, states are only defined as rays, and that's why you get CP, not CPW, but CPW minus 1. Okay, so it's a complex projective space. However, at the cost of a little bit of precision, you can in fact think of this Hilbert space as a sphere. Okay? So one way to visualize this Hilbert space is just to think of a sphere. Let me see if I can draw it. Right? Okay, so this is a Hilbert space. Okay. Okay. And so, in this Hilbert space, we are putting sum of AI squared equal to 1, which is what you would get for the Hilbert space. It's not completely precise because, we're also supposed to identify psi goes to e to the I theta psi. And so we are supposed to make an identification on this sphere, which is, if you look at, if you rephase everything, then you're supposed to get back the same state. But, that identification not very crucial. And therefore, you can visualize the Hilbert space as a big sphere. So the question I want to ask is, for a typical state, do these projectors jump on a single state? So, do these projectors project on a single state in the Hilbert space? No, not necessarily. The projector is just some projector. It's a, it's maybe you measure, I don't know, whatever observable, like the number operator or something. So the first question about the projectors. No. The projector is just a physical projector, right? So maybe you measure some physical observable. It has a spectral decomposition. And the projector just tells you the probability of getting one number. That projector could project onto half the Hilbert space. It could project onto the whole thing. It could project onto one state or 10 states or whatever it is, right? There's no such constraint. It's just a projector. Satisfies p squared equal to p. That's all. Yeah. Why is the Hilbert space CPW minus 1? That's just because, if I can, the way I specify a state is I give you W complex numbers, but, I have to identify the state by saying that, the set of complex numbers AI is the same as AI times Z, where Z is any other complex number. Okay? So it's not only enough to impose this norm, sum of AI squared equal to 1, you also have to identify AI with AI e to the I theta if you rescale everything. Okay? Or alternately stated, you give me a set of arbitrary complex numbers, and the set of distinct states are those, which cannot be identified by AI goes to ZAI. That's why it's CPW minus 1. Is that clear? I hope it's clear why it's CPW minus 1. Yeah. Okay. So the question we want to ask is, we pick a point, a random point, and that's our typical state. Okay. Okay. So to do that, I'm going to, to define a notion of random, I'm going to introduce the probability distribution on the Hilbert space. And the probability distribution, in fact, is very simple. It's the probability distribution is just this, okay? This is sometimes called the Haar random measure, where this V is set so that, the integral of d mu psi is set to be 1. Okay, so this V is some volume. You can compute what it is. If I have my notes correct, then this V is 2 times pi to the W by gamma W, but V is not going to appear in any calculation that we do. Okay. So this is some distribution, and the question I want to ask is, if I pick a random pure state with this probability distribution, so I just pick a point somewhere here or somewhere else, then what is, how is the expectation value of some other projector that I have going to compare to the expectation value in the microcanonical state? Okay, that's the question that we're trying to ask. Okay, good. So the first question is, right, so the difference we are trying to measure is psi p psi minus trace of rho p. So given that we have a probability distribution on the set of states, we can ask, what is the expected value for delta? This delta takes on various values in the Hilbert space, right? You give me a state psi, this guy always remains fixed. You give me a state psi, it takes on some value. You give me some other state psi, it takes on some other value. So it varies on this sphere. It has some value here, some value here, some value here, some value here. And we want to ask, what is the average value of this delta? Okay. Well, that's pretty easy to compute because you see, you want to compute let's look at psi p psi. It looks like AI squared plus some I not equal to j. These are the cross terms that we discussed. Yeah. So that's just some simple algebra. And now what we want to compute is the integral of this guy with d mu psi. That gives you the expectation, once I subtract off this thing, I'll get the expectation value of delta. Now it's pretty clear that if you want to look at the expectation value of AI, AJ star when I is not equal to J, those phases are going to be uncorrelated, right? In this measure is summing over all possible states. But clearly, if I is not equal to J, this is going to give you 0. So it's pretty clear that, integral of AI, AJ star d mu psi is equal to 0 if I not equal to J. What about integral of mod of AI squared d mu psi? Well, this guy is not hard to compute either, because you know that, if I sum over all of these AIs, I'm going to get 1, right? That was the normalization condition that we had. Therefore, and this answer clearly can't depend on I. Therefore, this must just be 1 over W. Okay? Therefore, we have found what the expectation value of this thing is. Okay? The expectation value of this thing is just 1 over W times sum over I, EI, P, EI. Okay, this is a side calculation, so let me put it to the side. Okay, but what is this? This is just a trace of P in the microcanonical density matrix. This is equal to trace of rho P. Because you see, what was rho? Rho was just sum of EI with a 1 over W factor. So this is exactly equal to that. What does this tell you? This tells you the expectation value of delta is 0. Okay. So first, the expected value of delta is just going to be 0. Okay. What does that tell you? It tells you if you compute the average of psi p psi in different points in the sphere, sometimes you'll get positive numbers, sometimes you'll get negative numbers. By the way, you always get real numbers when you do this calculation. P is a Hermitian operator. But the average will be 0. Now you might say, okay, why is that surprising? That's just some average. Maybe, I can still distinguish pure states from mixed states, because pure states, maybe they have average is 0, but pure states have positive value of delta or negative value of delta. And from the fact that, at any one point delta is not 0, I can check that pure states are different from mixed states. Question is, why did we choose that distribution? It's the most democratic distribution. We want to define a notion of typical, right? This is kind of the distribution that's saying, we pick a state, well, it's the natural volume measure that you would write down in the sphere, right? It's the natural measure you'd write down is this one on the Hilbert space. So it's a natural measure. And you're just saying, we want to pick, so you want to define what you mean by picking a state at random. So you want to say, you're not more likely to pick a state on this side than on this side than on this side, right? There might be some parts of the Hilbert space that are atypical. You don't want to say, I'm going to prefer those parts of the Hilbert space. So this is just a natural volume measure on the Hilbert space. That's why you pick this probability distribution. I mean, if you look at a sphere, there's a natural volume measure in the sphere. And that's this one. You're just summing over all AIs, and you're only putting the constraint that, sum of mod of AI square has to be 1. Now, is that clear? Yeah. Okay, great. So the expectation value of delta is 0. But now you might say, aha, expectation value of delta is 0, but I'm going to look at delta squared. You shouldn't have computed delta in the first place anyway, because, delta was of course going to be sometimes positive, sometimes negative. But, I can still distinguish pure states from mixed states by looking at the expected value of delta squared, right? If I do that, then I don't have cancellations between positive and negative numbers. So let's compute what this is. Okay. So we want to look at This is the expected value of delta squared. Okay, there's a little bit of algebra you can do. This is just some simple algebra. I'm just expanding out all of these terms. Psi p psi has an ej, ei, it multiplies with an ei aj star. This thing gives you the delta ij by w. Okay, and then there's one more term of this kind which looks like el, p, ek, ak, al star minus delta kl by w. Okay, and now you want to integrate this over d mu, and you need to sum over all of these guys. Okay, now notice that the integral forces must have I equal to j or k equal to l. That's kind of obvious. You can persuade yourself, that this integral is going to be 0 unless I is equal to j and k is equal to, and k equal to l, and k equal to l. Or I equal to L, K equal to J. Okay. So that's the only case in which you get some answer. And indeed, with a little bit of algebra, I'm not going to do this algebra, but you can do it as an exercise in doing multidimensional integrals. You will find that this looks like delta ij, delta kl plus delta il, delta jk, okay, by w into w plus 1. Okay. This is just a question of just doing this integral, and there are various ways to do it, and you will find this answer. Okay. Now, so you have to expand this, right? You see this delta ij, delta kl, everything is of this form. So you'll get this delta ij, delta kl term and delta il, delta jk term. You can check that, if you look at the delta ij, delta kl terms, okay, they give you a negative contribution to this integral. And let me explain why. You see, you have a delta ij, okay, and you get a delta kl from here. You have a delta kl and you get a delta ij from here. So you get a minus 2 by w into delta ij into delta kl. And that has, is contains with something which looks like 1 by w into w plus 1. Okay. Sorry, sorry, maybe I'll just do it. 1 second, please. Okay. So, if you look at what you get from here, you'll get some answer which will look like w.
Yeah. Just a moment before you proceed, in the previous slide, when you this expression for delta square, this TR P rho, why is it coming inside the integral? Because aren't we already in the trace accounting for this random measure? I'm not understanding. Oh.
This is the trace of rho. This rho is the microcanonical density matrix. Okay. This is the expectation value of P in a pure state. So delta tells you is a function of the state. It tells you how much the expectation value in a given state varies from the average expectation value, which is trace of rho times P. Okay. So this variation could be positive or negative for any state. Now what I want to do is I want to compute this difference. This is the average. This side is the average. I want to compute the difference and take the square and then sum the square. So it's the usual way we compute the variance. You take the difference of every value from, the microcanonical density matrix and square. This is a pure state. This is a mixed state. I'm asking how much does the pure state vary from the mixed state? So I'm taking the pure state, I'm subtracting off the answer in the mixed state so that, someone doesn't tell me you used positive and negative cancellations. I'm now trying to square the whole thing. It's a real number and then average it over all pure states. Okay.
Right.
Is that clear?
Yeah. Okay.
Okay. Is there any other question about what we're doing? Okay. Actually, sorry, you can check there's a little bit of algebra. Let me not do the algebra, but you can easily check that this delta squared, the expectation of delta squared, is smaller than equal to the term that you get, the contribution that you get with delta IL delta JK. It's a couple of lines of algebra. You can check that this term gives you always a negative contribution. Okay. So that contribution, the contribution that you get from delta IL delta JK is just this. Okay. It's some, sorry.
Well, where are the quartic terms?
Sorry, what happened?
Where are the quartic terms?
Here are the quartic terms: AI, AJ into AK, AL star.
Okay.
You see?
Yeah. And why when you have I and J different, it's 0? I mean the quadratic.
Why do you get this answer for the integral?
No, I mean in the previous slide, why when you have quadratic terms?
Oh, here, why did you get?
Different?
You mean here? Why did I get 0 when A and J was different? You see, because J can. You see, AI is one coefficient, AJ is another coefficient. Let's say I have some solution. I have some configuration of AI AJ, so that I'm satisfying the constraint that sum of AI squared is 1. Then there's another configuration which looks like AI, and I just flip AJ to minus of AJ, right?
Correct.
And therefore, this cannot have an expectation value on the set of all states. I can't tell you that, if I look at the set of all states, the coefficient of the first eigenvalue and the coefficient of the third eigenvalue are correlated. Because if I look at the set of all states and I'm averaging over all random states, then those phases are random, right? And therefore, you don't, it's just a question of doing the integral with that probability measure, but it's clear that this expectation value is going to be 0 unless I is equal to J. And this expectation value is going to be 1 over W. So that was the result we wrote here.
Thank you.
Is it clear? Because the phases are random, right? So I'm summing over random pure states, but typical pure states. But a typical pure state has a bunch of random phases. So the coefficients of different eigenvalues are not correlated. Is that clear?
Yes,
yeah,
it
there's
is.
one more question, I think. Yeah. Go on. Juan, you had a question? Yeah.
I think he has already asked this question.
You already asked. Okay. Okay, good. So is there any other question? Okay, excellent. So with some algebra, you can check that, it's dominated by this delta IL, delta KJ term, and that is just given by EI, PEJ, EJ, PEI. Shrink it. Okay. So that term, collapses the sum to the sum of these two variables, and you get this. Okay. However, notice that this EJ, it looks like a sum over a complete set of states, but in fact, it's not a set of complete states because this EJ is just running over the microcanonical density matrix. Okay. So this sum you can check because this is some positive operator. You can check that this is in fact smaller than or equal to sum over I, EI, P squared, EI. Okay. The reason it's smaller than equal to and not equal to is because this EJ is summing over the microcanonical density matrix, which is not the space of all states in the Hilbert space, but a subspace. Okay. But you remember P is a projector, so P squared is just equal to P. So this is just equal to not only is P a projector, because it's a projector, it can have no eigenvalue larger than 1. And therefore, this is smaller than or equal to W. Okay. What have we proved? What we've proved is that delta squared is smaller than or equal to 1 by W plus 1. Okay. Now remember that W was e to the s. Okay. And so so what have we proved? What we've proved is that the square of the deviation, the expectation value of the square of the deviation is e to the minus s. Okay. So the expected square of the deviation is e to the minus s. So the expected deviation is e to the minus s by 2. So this is actually a pretty important result. This simple result that we proved in statistical mechanics is an important result. It's used all the time, when we discuss quantum information about black holes. And it is telling us that pure states on average look exactly like the microcanonical ensemble. By the way, the reason it looks like the microcanonical ensemble is because of the way we picked our set of pure states, right? We picked them from being strictly in a certain energy band. You could pick a set of pure states that looks like the canonical ensemble, if you like the microcanonical ensemble, and the deviation and the average deviation for any observable. Notice I made no assumption about what the observable was. So any observable is order e to the minus s by 2. Okay. This is a very important physical result. Okay? So this is telling you that, for any observable, most states look almost exactly like the mixed state. Now, there could, of course, be some states that are atypical. It's not that there are no states which are atypical, which could have big deviations. But, we also learned that the volume of atypical states is exponentially small. Because if the volume was not exponentially small, they would contribute and they would change this integral. Okay. So these are very important physical results that you should really understand. Is there a question? Go on.
Yeah, any observable, the R projector, right?
Sorry, can you say again?
Any observable, the R kind of projector,
Well,
because
that's what I said at the beginning. In quantum mechanics, the only observables are projectors. We speak of general Hermitian observables, but Hermitian observables have a spectral decomposition, and what we really measure by the Born rule is the expectation value of a projector. So there are. It's not like there are other observables that you can measure. The thing that you measure when you make a quantum mechanical measurement is the probability distribution that you get always corresponds to expectation values of projectors. I mean, the reason I wanted to emphasize this was it's not that there are eigenvalues, but those are the probabilities of different outcomes. The eigenvalues tell you the outcomes, but the probabilities are given by projectors.
Okay, thank you.
Is it clear? Is the answer clear? I'll assume it's clear.
He said it's clear.
Yeah, okay. The result, no, there's no Planck's constant here. There's no Planck's constant here. It's just e to the minus s. Yeah. I mean, s was just the number of states. So there was no Planck's constant here. Can we somehow say projectors are density matrices? No. Projectors are not density matrices. I didn't say. Projectors are just projectors. They just project onto some space. Some pure density matrices might happen to be projectors, but in general, density matrices and projectors are different things. The reason I was talking about projectors are because of quantum mechanics, which tells us that when we look at expectation value of observables, we are really looking at probabilities of getting different answers, and those probabilities are given by expectation value of the projector. So when you have a Hermitian observable, you do a spectral decomposition as sum of lambda I OI, sum of lambda I PI, and then you look at the probabilities of the different projectors. Kiran asks, can we not use the trace norm? You mean the trace norm between the pure state and the mixed state? What is its physics? It does not have a physical interpretation. If I have a state, like this room, I cannot compute the trace norm of its density matrix with, some other density matrix. That's not an observable that an observation we can do. The observation we can do is I can measure something, like I can measure the temperature. And quantum mechanics tells me I'll get different values for the temperature. And what I can note down that probability distribution. So that's why I was important in saying when we ask for when something is close or not, we want to ask what are the probabilities of a physical experiment, of outcomes in a physical experiment. So the trace norm is mathematically well defined. If I did all possible experiments, then I could determine the full density matrix and then look at the trace of that with something else. But for that, I have to do an exponentially large number of observations because I have to determine all density matrices, all matrix of the density matrix. Yeah. So this is a physical notion of closeness. What happens if you make a quantum mechanical measurement? Yeah. Okay, are there any other questions? So what is the picture that we arrived at? Yeah, the picture that we arrived at was, let's fill it. The picture we arrived at was that this was the Hilbert space, and then there are some small atypical spaces.
Before you proceed, the second condition on the previous slide was the second statement that you've written is more of a precondition, right?
No. It's not a precondition. You see, we proved that mod of delta square was smaller than this, right? So if there were atypical states where the variation was much bigger, was say 1. Clearly, if there's an atypical state where delta is equal to 1, the volume of that has to be small. Otherwise, you would not, delta square is positive. So if you're going to get that expectation of delta square is 1 by e to the s, it cannot be that the volume of atypical states is order 1. If it was order 1, you would already, find expectation of delta square was order 1, not order e to the minus s.
So the atypical states are being accounted for in the measure that we chose.
Absolutely, because all states are being accounted for.
Yeah. So I don't know, maybe I missed the definition of what the typical state is, but like
a typical state just meant so what I was saying was I'm always computing this expectation. I'm computing delta, and I'm trying to ask how does delta vary over the space of all states. So I'm trying to. I have introduced a probability measure on the Hilbert space. It's called the Haar measure, and I'm trying to ask how this delta varies on the full Hilbert space. Maybe it'll be clear as I say this. Let me say a little bit more. You can ask again. Yeah. So this is the picture that we found, right? That we have the Hilbert space. This is a picture of the Hilbert space. I said it was a sphere. And most states look exactly the same from the point of view of any measurement. You make any measurement, most states are the same. They don't look different. They look the same as each other. And they also look the same as the microcanonical density matrix. There are some atypical states, but they're very rare and far and few in between. Okay. What is atypical for one measurement might not be atypical for another measurement. But let's say you pick up a particular set of measurements you want to do. Then on most of the Hilbert space, you'll find the same answer. On some isolated points, some small, exponentially small volumes, you'll find different answers. But that place where you'll find different answers is very small. Okay, so that was the result I wanted to present about this. I don't know if this answers the previous question you had about what I was saying. It's a very physical question. Take this room, look at the set of all possible states of the room, measure the temperature, and start asking what you'll get in different states. In most states in the Hilbert space, you'll get the same answer up to exponentially small deviations. In some places, you might get different answers, but those places are exponentially small in the volume of the Hilbert space. Okay. So this intuition is very different from the intuition that we have for low dimensional spaces. Okay, this sometimes leads to a lot of confusion. If you think of 2-qubit systems or a 1-qubit system like the one I started with, where the cat was happy and small, pure states were not the same as a mixed state. Pure states could be easily distinguished from mixed states. Okay, but this is a feature of high dimensional spaces. In a high dimensional space, most states are featureless. What does that mean? That means that, if you pick a set of observations ahead of time and you say, this is what I mean by feature, then, most states will just give you the same answer for all those observations. There'll be some states, of course, that will be special. but most states are just featureless. Okay.
Yeah, in fact, this is I wanted to ask. So this result it's applicable like when you have a lot of number of states. Like
Correct.
The state. Correct.
That's right. It relies on having a large number of states because what was small here was everything was e to the minus s by 2. So it's very important that e to the s was large. Otherwise, this result, this could be order 1.
Thank you.
Yeah. Okay.
Someone asked about the definition of dimension there.
Yeah, dimension of Hilbert space. Absolutely. Yeah. Okay. Let me say a few clarifications. Okay, so possible confusions. Okay. This is one possible confusion. Let's say we take a system of n qubits. Here's the basis of this system of n qubits, right? And look, it's 0, 0, 0, 0, right? Just the different binary numbers. And then you have n qubits, you have some 1, 1, 1, 1. Okay. Now you might say, let me look at sigma z I. Clearly, all these states are very different, right? All these states are eigenstates of sigma zi. If I measure sigma z1 for the first state, I get 0. For the last state, I get 1. This is obviously different from a mixed state. What would be a general mixed state? A mixed state would be a probabilistic answer for all of these guys. Sorry, maybe it's just for which I'd always, sorry, if I want to use sigma, I should use -1 and 1. I'm using 0 and 1, but if I use if this is my, if I just look at sigma z plus 1, then, for a general state, I expect to get half. I don't expect to get either 0 or 1, right? So clearly someone might say, look, these states are all very special from the point of view of, measurements of the value of this qubit, which I'm calling sigma z. Okay? But let me remind you that this is the basis. Let me remind you, this is true, of course. These states are very atypical from the point of view of measurements of sigma z. Okay, so these are atypical states. You might say, look, but atypical states form a basis. And that's fine because basis states take up 0 volume in the Hilbert space. Okay. So the fact that you can find an atypical basis doesn't mean that, most states are atypical. Many bases are atypical. You can choose a basis with respect to a set of observables and the basis is atypical. But the set of basis states is volume 0 in the Hilbert space. Do you see why? Because, a basis state is one state in the Hilbert space. The Hilbert space, as I said, is a copy of CPW minus 1. If there are W basis states in this Hilbert space, but that's just W points. Okay? If you try to look at the volume, you try and pick a typical state in the Hilbert space, you're not going to pick a basis. Okay? So even sometimes you'll find papers in the literature that will say, look, pure states are different from mixed states because, here's how they're different. Take a system of n qubits and look, this is a pure state, an example of a pure state, and look, it looks different from a mixed state where I get the value half. But this is wrong because this is a very atypical set of pure states, which are basically volume 0 in the Hilbert space. And it's true, of course, if you pick a basis of observables, there are some states which are atypical, but most states are not like this. Okay, most pure states are not like this with respect to sigma z. For most states, in fact, you will get the value half if you take some superposition for almost all states. And this happens to be a space of volume 0. Okay. So, please, next time you see a paper in the literature that tells you pure states are different from mixed states and gives you this example, you should stop reading the paper at that point. Okay, good. Here's, second possible confusion, okay, which is ETH. Sometimes people talk about the eigenstate thermalization hypothesis. The eigenstate thermalization hypothesis is an important result, but our result did not invoke the ETH. It's a kinematical result. Yeah, just a second. Okay. And the reason our result was, works is because we are saying we want to look at typical pure states. If you look at typical pure states, you don't need the ETH to say typical pure states look like thermal states. The ETH is a statement that if you pick an individual energy eigenstate, then that individual energy eigenstate also is supposed to look like a thermal state for some observations. But you see, an individual energy eigenstate could be very atypical. As I said, just explained, the basis states in fact occupy zero volume. So it could be that, what we prove doesn't prove that individual energy eigenstates look like thermal states, and that's what the ETH is addressing. But the ETH is addressing a different question. We did not need the ETH because we were looking at typical pure states. Okay. Yeah, go ahead. Your question. Sutant has your question.
Yeah. So the derivation of this previous section about the deviation between pure and mixed states was done starting with the microcanonical density matrix.
Yes.
But would you say that in the large dimension of the Hilbert space limit, it could be generalized to, like, say, the canonical and the other sorts of ensembles?
It could be, but we chose both our states and our density matrix to be microcanonical. Let me just go. Yeah, you see, we chose this. The density matrix we were comparing was this. This was microcanonical. But look at the set of states we compared was sum of AI, EI, where so it was also strictly banded. Now you could say, I want to look at not this class of states, but a class of states where all energies are allowed, but the size of the coefficient has to be e to the minus beta h or something. You could say something like that. So this, I'll allow even arbitrarily high energy states, but they're, I'll assume they're suppressed. Their coefficients are suppressed. Here, what we were doing was we were looking at all kinds of states where these AIs were, the same as, were basically being picked with equal probability in this band of energies. So this was a set of pure states, which was kind of geared to compare with the microcanonical ensemble. If you wanted to compare the canonical ensemble, there's a different set of states you can look at, where you basically have to look at pure states where you draw from all energies, but with the right probability distribution. And if you do that, you'll find the same result for that case.
I see. Okay. So in that case, so it seems that we are taking some sort of a cue from the kind of ensemble that we're working with to find the corresponding set of pure states that we think is a natural comparison.
Sure, that's right. That's right. So this, the set of pure states is just, set of pure states. If you want exponentially close things, by the way, if you're happy with closeness at power law level, you don't even need to do this, right? Because then all these ensembles are the same. They're all the same up to answers which depend at, if you want that vary by 1 over s. So it's true, if you want exponential closeness, an ensemble corresponds to a particular set of states, right? And that's, this ensemble is defined by sharply cutting off states outside this energy band, and so is the set of pure states that we have. So this set of pure states looks the same as this ensemble up to exponential closeness.
Okay.
Okay, as I said, you could look at other sets of pure states. So they would look the same as other ensembles up to exponential closeness. Okay, good. So this is about the ETH. Let me also say one thing about the entanglement entropy. This is another thing. Well, entanglement entropy can always distinguish pure and mixed states. Always. Right? Why? Because, the entanglement entropy for the case that we're looking at. So if I look at S entanglement of rho, which is minus trace of rho log rho, well, this is log of W. Okay. And if you look at S entanglement for any pure state, this is 0. You might say, aha, how did this happen? How is the entanglement entropy or the von Neumann entropy? Here, there's nothing to be, by entanglement entropy, I just mean trace of rho log rho, okay? Which is the von Neumann entropy. You could say, how did this happen? The entanglement entropy is 0 for all pure states. It's log W. How is this consistent with the result that we have? Well, let me remind you, the von Neumann entropy or the entanglement entropy is not the expectation value of any observable. So the entanglement entropy is not by itself an observable. Okay, this is another important information theoretic result to know. Let me prove this for you. For those of you who have not seen this proof, maybe many of you have. Say there's some observable so that S ent is the expectation, is given by the expectation of A. Okay, say that there existed some linear observable which had the property that the entanglement entropy was the expectation value of the observable. The entanglement entropy or the von Neumann entropy is always positive. So it must be the case that A is larger than or equal to 0. Okay? But A is equal to 0 on disentangled states or on pure states. So trace of A is equal to 0 because disentangled states give you a basis for the Hilbert space. But if you have a positive operator and its trace is 0, this implies A is 0, but that's absurd because the entanglement entropy is not 0. Okay? This is just a standard proof that tells you that the von Neumann entropy or the entanglement entropy is not an observable in the sense of quantum mechanics. Rather, it's a function of correlation functions. You can think of Sent as a function of correlation function. So, if you give me other observables, I can put them together and determine the entanglement entropy. But the entanglement entropy is a very fine-grained object, and it's not just any function of correlation functions. I want to add a qualifier here. So let me move to the next thing. And that is sensitive to exponentially small effects. Okay. So it's a very fine-grained observable from a physical point of view. Sometimes it might be very easy to mathematically compute the entanglement entropy. But from a physical point of view, you should know it's a very fine-grained observable. Okay. And that's because pure states, and what we're saying is very physical. If you take the edge of this galaxy and you disentangle it from the rest of the universe, the galaxy will go into a pure state. But if we make an observation here, we are not expected to know whether the galaxy is in a pure state or a mixed state. But the entanglement entropy of the galaxy will know. And that's because the entanglement entropy is a function of correlation functions. It's sensitive to small effects. Okay. Okay. So that ends the statistical mechanics lecture I want to give. I'm now going to turn back to the information paradox, but are there any questions about the statistical mechanics part? Is this clear to everyone what we said? Okay, if not, we can always discuss more questions next time. Okay. Let me now ask, what is the relevance for the information paradox? Why did we have this long detour into statistical mechanics? Well, one reason was because what I said right now is useful for other things also, not just for the information paradox. So, you should know what I said right now. It's some standard material in statistical mechanics, but it's very relevant for the information paradox. And that's because, remember, what Hawking computed was this. And then he concluded based on this, well, actually, he had more arguments, but the simplest version of the Hawking paradox says, aha, look, these 2-point correlators look like thermal 2-point correlators, therefore the state is mixed. But now we know that's wrong, because if you just allow me to add some small corrections here, then that will can make these correlators consistent with a pure state as well. In fact, not only that, I expect that in a pure state, I will get the same correlators that I have in the thermal state. So it's not surprising that when you compute this simple observable, you found these correlators that you should have found. because you do expect that even in a typical pure state, this is exactly the answer you would have got. And you would only start seeing differences if you kept track of these corrections of order e to the minus s by 2. What is S here? Well, S here is the black hole entropy. Okay, which is huge for all the black holes that we are looking at. Okay, and therefore, in what we have done, or in Hawking's calculation, does not keep track even of 1 over s corrections, or 1 over square root s corrections. Why doesn't it keep track? For instance, imagine that we prepared a black hole in the microcanonical ensemble rather than the canonical ensemble, in which case the black hole wouldn't have a temperature, but rather we said it was a bunch of energies. Well, we already know that, there's a difference between the expectation value you get in the canonical ensemble and the microcanonical ensemble, and that difference is 1 over square root s. But in the Hawking computation, you don't see even this difference, because to keep track of this difference, you would have to keep track of fluctuations in the geometry that are 1 over square root s. Okay. In fact, this s is very closely tied to the, what gives rise to gravitational corrections. And that is because if you take E, if you consider the parameter which is G Newton times T to the D minus 2, this is the temperature. And remember, this is the same as 1 over S. Okay? So you see gravitational corrections or quantum gravity corrections in this setup are precisely controlled by this parameter, which is G Newton times the temperature to the D minus 2. That's because all gravitational corrections come with G. And what is the dimensionful parameter you could assign to get a dimensionless parameter? Well, it's the temperature to the D minus 2. And therefore, if you were to try and compute gravitational loops or loop corrections in this geometry, they would all come with this parameter, which is 1 over S. So, in Hawking's result, we did not keep track of this. This you can see in many different places. We assumed there was a geometry. We assumed that the geometry was not fluctuating. But the geometry does have fluctuations. If you're in the microcanonical ensemble, the fluctuations of the geometry would be different from the fluctuations of, of the geometry in the canonical ensemble. We never kept track of those. We certainly didn't keep track of exponentially small corrections. At the beginning of this lecture, there was a question about non-perturbative corrections. Even if you were to allow me to add only non-perturbative corrections, that would be enough to make Hawking's result consistent with that of a pure state. Okay. So the bottom line, and this is something to remember, is that the computation of Hawking radiation is not precise enough to lead to a paradox. Okay. Now, this doesn't mean there's no paradox, but it just means that this computation, and in fact, as I'm about to explain in a minute, Hawking himself had an argument, had a counter argument to this. But this computation, sometimes you will find popular descriptions of the paradox. Sometimes in my own popular lectures, I say, look, you can compute this paradox. You find that the black hole gives thermal radiation. The thermal radiation is uncorrelated with the initial state. Therefore, you get a paradox. But this is not precise enough to lead to a paradox. And the whole point of our long statistical mechanics song and dance was to show that pure states look the same as thermal states. Therefore, by computing low point correlators or computing one observable or a small set of observables, which is what we compute in the Hawking result, we compute observables which correspond to the expectation value of the number operator at Scri plus. This expectation value cannot distinguish between a pure state and a mixed state unless you keep track of exponentially small corrections. Okay. So this is the first major conclusion that I wanted to reach. Okay? Now I want to go on and discuss more sophisticated versions of the paradox. In fact, including the version that Hawking himself outlined. So Hawking himself was aware of this issue. Okay? It's not like Hawking was not aware of this issue. In fact, and this is not always realized. So I now want to, in fact, open Hawking's paper and look at more sophisticated versions of the paradox. But this is the first conclusion that I would like all of you to take away from this course, because it's a simple conclusion. It just relies on simple properties of understanding what was Hawking's calculation and understanding some simple statistical mechanics aspects. And that already is enough to give you this result. Okay. Okay, let me stop here for questions, and then I'm going to tell you, how you can refine the paradox, and then we'll have to come up with better arguments to resolve it. Are there any questions here? Already in 1975, Wald provided a more complete calculation that included the computation of the state of the field rather than only the expectation value. As far as I know, there's no computation. The state of the field is something that you actually need to specify. It's not something that you can compute. For instance, this difference between the microcanonical and the canonical ensemble is something where you need to specify, you need to specify what the state of the field is. And the state of the field would be one thing in the microcanonical ensemble and a different thing in the canonical ensemble. So sometimes, people, I'm not sure which paper you're referring to, but there are many computations, of course, you can do, in flat space and so on. But to specify the state of the field in the black hole geometry is already something that involves something of a choice. And you would already start seeing that the radiation would be sensitive to that. But unless you could keep track of non-perturbative corrections, let me emphasize, it's not sufficient just to specify the leading 2-point corrections. Unless you can keep track of non-perturbative corrections, you would not be in a position to reach a paradox. Okay? If you want to explain your question more, you can go ahead and do that. Yeah, go on.
Okay.
Why don't you go ahead? Yeah.
Yes. What I'm thinking about is the usual computation that I'm aware of. For example, as in Wald's paper, it is on particle creation by black holes, and I think he also reproduces it in his quantum field theory in space-time book. He reaches a final state for the field, and I think he does that by assuming that you are in the Unruh vacuum.
Yeah.
So
it's not enough, because notice you also need to keep into account the fluctuations I'm talking about are fluctuations of the geometry. So remember, where did the surface gravity come from? The surface gravity came from the fact that the geometry, the metric, had some form which looked like, du dv times some factor which depended on the surface gravity, right? So there was some factor which went in there. If you do quantum field theory in curved space-time, you can do quantum field theory in curved space-time, till kingdom come. It will never give you these fluctuations, will not even give you these 1/s corrections that differ between, the canonical and the microcanonical ensemble. Unless you keep track of the fact that the metric itself, the background metric itself is fluctuating. Do you see how that entered here? I wrote down a background metric, which was G mu nu, right? Which looked like G mu nu, dx mu, dx nu. But in the quantum theory, this itself is an observable. And actually, I cannot compute about one background metric. Rather, I have to tell you what the wave function of the background metric is. Okay? And then about every such wave function, I can do this calculation. So if this wave function has some fluctuations in the background metric, which in fact you expect it to have, as I said, these fluctuations are different in the microcanonical and the canonical ensemble. You will start seeing characteristics of this wave function in the characteristics of the final state at infinity. This calculation is a very hard calculation to do, and that's why it's not been done. But, in quantum field theory in curved space-time, which is the calculation that I recall, you would never see this because you're not even specifying the wave function of the metric. Okay? Even the difference between canonical and microcanonical, as I said, you have to specify the wave function of the metric. Okay? So
I understand.
So this is not been done as far as I know in the literature, and it's not surprising it's not been done because it's a very hard thing to specify, right? You have to specify the wave function of the metric. You have to show it obeys the right constraints and so on. So it's a very hard calculation to do. Not surprising it's not been done. But if we were to do it, you expect you would immediately start seeing corrections at 1/s because the fluctuations of this wave function are this size. And so you can estimate what kind of corrections it would give you. And no one's kept, you can't keep track of them in some systematic or easy way.
I see. Thank you.
So yeah, the calculations, people often do calculations of QFT in curved spacetime. And of course, you'll get a wrong result if you do that, if you haven't, because you're ignoring the physical fluctuations in the geometry.
Mhm.
Okay, good. So now this is the first result. This is a very robust result, what I said. However, something which people don't realize, which in fact, I must admit, I also didn't realize when I first started writing, thinking about the information paradox. So if you open some of my old papers from 10 years ago, you will find, the incorrect suggestion that, Hawking himself was not aware of this issue. In fact, Hawking was aware of this issue. And so what I want to do now for the last 15 minutes is share screen and show you what Hawking's paper was. And so I'm going to share from my computer instead of, how do I stop share? Yeah. So let me share instead from my computer. Yeah. Okay, so I want to show you how Hawking, in fact, himself raised his paper. Okay. And I want to tell you that Hawking's paper, so we'll just read this paper for 5 or 10 minutes, and then I want to emphasize what Hawking's argument was, okay? This is Hawking's paper. So in fact, Hawking has two famous papers in this. One of them is where the computation of black hole radiation is done. This is not that paper. This is the information paradox paper, okay? So this is the breakdown of predictability in gravitational collapse paper, okay? It's after the paper on Hawking radiation, okay? So let's just look at the abstract. Okay, so principle of equivalence, blah, blah, blah. And then it says in this paper, it is claimed the breakdown is not just ignorance, but represents a fundamental limitation. Okay. And then look what he says. He says the new limitation arises because GR allows the causal structure of space-time to be very different. And he says the interaction region, which is the region where you have black holes in modern terminology, is covered by a hidden surface. Hidden surface in modern terminology, we would say is the horizon, or is the part of the Cauchy slice inside the horizon in modern terminology. And he says the observer would have only limited information about what's happening inside the black hole, and only would know about the mass, angular momentum, and charge. Okay. And most importantly, he would say concerning this hidden surface, one has a principle of ignorance. So you can open this paper, and I recommend that all of you should read it. And if you read the paper, you will find a lot of importance is given to this principle of ignorance. Okay? And in the end, it's shown that this ignorance principle holds for quantum mechanical evaporation of black holes. So what Hawking was actually saying, if you read this carefully, is he wanted to say, fine, I did a calculation, or at least I think he wanted to say, I did a calculation of, Hawking radiation, of this radiation. Maybe the calculation is corrected, just you tell me it's corrected by 1/s, fine, it's corrected. However, he wanted to argue that if you postulate this principle of ignorance, then in fact, the final result that the state is mixed is robust. So he wanted to say, which is related to, in fact, something that was asked in a question in the earlier part of the talk, maybe the final state is not the thermal state, maybe that state is corrected. However, he wanted to say it will still be the case that the final state is mixed. So I'm now going to take you a little bit down in the paper. We won't go through the whole paper, and I'll show you where the key part is, okay? Here's the key part where he makes the argument that the state is mixed. He says, let H1 be the Hilbert space of all possible data on the initial surface. So, here's the picture you should keep in mind. I'll draw it on this side, okay? So this is the Penrose diagram, okay? This is the horizon, okay? And I'm trying to draw with my mouse, so it's not very, sorry, let me erase this. Let me start again. Okay, this is the horizon. And what is the initial surface? So I want you to focus on this paragraph here. Yeah. The initial surface is this surface here. This is where you specify the data H1. Okay, this is the initial data. What does he mean by the hidden surface? The hidden surface, H2 is the data on the hidden surface. This he means you draw a Cauchy slice, think of some surface here, and H2 is the part of the data that you specify inside the horizon. That's why it's hidden. Okay. So in modern terminology, we would say you have a nice slice, and the part of the nice slice that's behind the horizon is, well, you know, he's using natural terminology, it's hidden from the observer outside. And H3 is the data outside the horizon. Why is this also the final surface? Because if you look at the causal structure of space-time, this is the data that propagates out to Scri plus. Okay. So is this clear what he's saying? You know, H1 is the data on the initial surface, which is this. H2 is the data. H3 is the data here. Then he says, a basic assumption of quantum theory, and I want to point out because, you know, this is also going to be the part which is going to turn out to be wrong. So there's going to be an error here. But a basic assumption of quantum theory is that there's some tensor ABC which says that which maps this surface H1 to H2 cross H3. Okay. So he wants to say the final Hilbert space factorizes into H2 times H3, and there's a unitary map that goes from H1 to H2 times H3. That's what he's saying here. This tensor SABC, this is the S matrix, but notice the S matrix has two legs, one in the final surface, one in B, one in C, sorry, one in A, one in B. So he's saying the Hilbert space factorizes into H2 times H3, and that's the S matrix. Then he says, look, the observer outside cannot know anything about the hidden surface. So this is the part here. The principle of ignorance says that all field configurations on the hidden surface are equally probable provided they're compatible with the conservation of mass, angular momentum, etc. This is the statement of the no-hair theorem. It says that in the classical theory, all you can know for an observer outside is the mass, charge, and angular momentum. Therefore, he says the person, you know, the observer who's making measurements in H3 must trace over H2 with equal probability because they have no information about H2. And obviously, you know, if you take a state that's defined on H2 times H3, and you trace over H2, this is the principle of ignorance, you will get a mixed state in H3. Okay? Is it clear? You know, even if you start with a pure state in H2 times H3, and if you trace over H2, you will get a mixed state in H3. And the key part is this part. Okay, so pay attention to this part. He wants to say that the only data you have in H3 is the total mass, charge, and angular momentum of what is inside H2, and all other field configurations are equally probable. Okay. Okay, is this part of Hawking's paper clear? So what Hawking was saying was, you know, if you look at this argument, you see it doesn't rely so much on the precise calculation that there's a thermal Boltzmann factor or so on. What he's saying is, forget that, you know, fine, you know, there's some calculation I did which shows some thermal thing. You say it's corrected, I'll accept it's corrected. But look at the causal structure of the space-time. The causal structure is such that the infalling matter is somewhere here, right? And all you know outside is the total mass, charge, and angular momentum. And this part of the space-time is going to disappear. Sometimes people do an extended Penrose diagram. It doesn't matter for making this argument, because this part of the space-time is never going to be causally connected to Scri plus. And therefore, the observer at Scri plus has to trace over everything that went inside. Okay? Because they only know about the mass, charge, and angular momentum. Okay. So the flavor of this argument is a little different from the argument saying we did a calculation and we found the radiation was thermal. And in fact, if you open Hawking's paper, this was Hawking's argument. So you see, it's a slightly more robust argument than the popular description of the paradox, which is we do a calculation, we find it's thermal, therefore the state is thermal. Okay. Okay. Is this argument clear? I recommend that all of you open Hawking's paper and read it. We won't read the whole paper in the class, but you can read it at your own leisure. Yeah? But these are the key points I want to emphasize in Hawking's paper. Yeah, your question, yeah.
Yes, the Penrose diagram that we are seeing is the same or almost the same for any black hole?
What are you saying? Sorry, can you
The Penrose diagram
the Penrose
that we
diagram,
have
yeah,
here.
we addressed this in the beginning. It's qualitatively the same for any black hole. You know, if you look at a Kerr black hole or a Dyson-Ostrom black hole, there's a naive Penrose diagram you can draw that looks different. But in fact, once you take care of the instability of the inner horizon, all these Penrose diagrams are qualitatively the same. They're slightly different in detail, but you know, there's some additional fancy Penrose diagrams you get for a Kerr black hole where you can go off into another universe and so on. Those are actually fake. In fact, the space-time effectively ends at the inner horizon. For anything that's a slight perturbation away from the pure Kerr geometry, the space-time will end. And so all these Penrose diagrams are indeed the same if qualitatively the same for all black holes.
So we can always make this tensor product of H2 times H3?
Well, as I'm going to explain in the next two lectures, this is wrong in a theory of gravity. This tensor product factorization, which would be correct in a non-gravitational theory, is demonstrably wrong in a theory of gravity. Also, it's demonstrably wrong that in quantum gravity, you only know about the mass, charge, and angular momentum. That's a classical result. And I'm going to explain to you why Hawking's error was to assume that the classical result holds also in the quantum theory, to carry over classical intuition to the quantum theory. But this is, for now, what Hawking is saying.
And I have another question. It's about the surface gravity, because we have seen a background metric that is almost Schwarzschild. But here we are talking about angular momentum and electrical charge. So we have a Kernium black hole. I think.
You would change the detailed formula for the surface gravity. You know, the formula for the temperature would be slightly different, the details, but you know, you would still find a temperature.
But it is still related to the derivative of FR?
Yeah, sorry. The curve metric doesn't have the form that we wrote. You know, the form that we wrote looked like f of r times dr square. We assume in the precise metric we wrote, we assumed a spherical symmetry in writing down the metric. Yeah, you know, in any textbook on GR, you'll find the formula for the surface gravity for the Kerr-Newman black hole. These distinctions are not important. You know, the importance in all of these cases, you always have a temperature. But you know, the precise formula is different. You'll find it in any GR textbook. It's not in the formula I wrote down in the class. I assume Schwarzschild for simplicity. So that formula doesn't generalize. It doesn't even make sense if you don't have spherical symmetry. But you will find the formula in any GR textbook. But as I said, qualitatively the Penrose diagram is the same, and so in terms of the information paradox, there's the same information paradox for all black holes, for all kinds.
Okay, so for calculating the surface gravity, the main quantity is temperature.
The surface gravity, that's right. So, you know, what we want to look at is the temperature. But what I want to emphasize here is that in these words, in this formulation, the surface gravity is not appearing. Notice here. The point I'm trying to make here is that Hawking's argument did not rely on the calculation that it was 1 by 1 minus e to the minus beta omega. The calculation that the argument that Hawking is giving for the information paradox is based on the causal structure of the space-time, which is that look, the initial state on H1 is defined, goes to a final state on H2 times H3, and the observer outside has a principle of ignorance about H2, and therefore they have to trace over H2. So, you know, the important point is that we are now going to a version of the information paradox where the details of the surface gravity are not going to be important. As you can see, they're not important here. They don't appear on the screen, which is where the key argument is made.
Okay, thanks.
But that being said, the answer to your question, you'll find there's a formula for the temperature, and that temperature formula you can find, you know, is a simple function of mass, charge, and angular momentum. I can write it down at the beginning of next class. Yeah, Harpreet, your question, yeah.
Yeah, sir. In the last lecture, you told that there is nothing, means the time and space, they won't change actually the sign and they won't change anything. It's because of the coordinate system only, isn't it?
Yes. Yes.
So now, but Hawking is saying something about the hidden surface. It
Yes.
shouldn't be like that. It's just a matter of coordinate system, isn't it?
No, no. The hidden surface is something which is defined because the horizon is defined as the boundary of Scri plus. The hidden surface, is telling you that the data here is always causally disconnected from the data here. So what Hawking is saying is if you define the final data on Scri plus, which is this part, that's causally disconnected from this part. That's not a local statement about something happening across the horizon, but the horizon is important for the global causal structure. So what Hawking is saying is look at the global causal structure of the space-time, and data here never looks like it's always space-like disconnected from data here. Therefore, the observer who lives in H3 only has information about the mass, charge, and angular momentum.
Yeah.
Okay. So what I want to emphasize at this point was the following. Let me stop share. Yeah, I want to emphasize the following point, and then we can stop since we're out of time. The point I want to maybe I can share briefly just to write the points. Yeah, this because oops, sorry. Where is this? It's here. Sorry. So the point I wanted to emphasize in this discussion, I don't know if you can see my screen. Can you see my screen actually?
Yes.
Do you see my screen?
Yes, you can see the black board.
I don't see it again, but there's obviously some problem with my. Anyway, never mind. The point I wanted to emphasize was that Hawking had a more robust argument based on the principle of ignorance. What was that principle? The principle was simply, if you look at a black hole space-time, this is the horizon. Okay, then the observer here, the observer outside only knows about mass, charge, and angular momentum. Of the state inside. Right? This is the principle of ignorance. Okay, what I'm now going to explain to you in the next couple of lectures, and this is another important feature of quantum gravity, which you should know again, is that in a theory of quantum gravity, we will replace the principle of ignorance with a principle of, information. And I'll make this more precise. And in fact, we'll find if you keep track of exponentially small effects, which of course you have to, right? Then the observer outside has information about everything inside, and this factorization of the Hilbert space that Hawking assumed. So Hawking assumed that the final state Hilbert space factorizes into H2 times H3. This is some assumption that comes from quantum field theory. This is some assumption that comes from the classical GR, and combining this intuition leads you to wrong results. And we can show that in theory of gravity, the Hilbert space does not factorize this way. And it's not true that the observer outside only knows about the mass, charge, and angular momentum. But that is something we'll discuss next time. But I want to end this lecture. Let me just summarize what we said so far. What we said so far was that, if you look at, just look at the computation of Hawking radiation, that is not precise enough to lead to a paradox. It's not precise enough to lead to a paradox because pure states are exponentially close to mixed states. This is a general result in statistical mechanics. However, Hawking had a counter argument to this. He said, fine, maybe you will have corrections, but in the case of a black hole, the corrections will never convert the mixed state to a pure state. And the reason for that is if you look at the causal structure of the space-time, which is very robust, he says, and you use this principle of ignorance, which is robust, he says, because it's based on, the no-hair theorem and the fact that the observer outside is causally separated from the data inside, then you would reach the conclusion that the state was mixed. Even if it wasn't exactly the mixed state that one gets by doing Hawking radiation, it would still be mixed. So that's the more sophisticated version of Hawking's paradox, and we'll see next time how that can be resolved, and how, in fact, the Hilbert space and gravity doesn't factorize. And this is another important aspect of quantum gravity that one should know about anyway. Okay, but since we're out of time, I'm going to stop here and see if there are questions. If there are questions, I can take them now. Or we can. No, it's fine. Yeah, as you like. We can, it's up to you here. Sorry, I'm having some problem with Zoom on my computer, so I can't see things in the chat anymore, unfortunately. So if there's a question in the chat, you're going to have to read it out to me. Could you go back to the slide with references I gave at the beginning of the lecture? Yeah. Yeah, sure. Yeah. So, most of what I'm speaking about in the first several lectures is based on this long review, which is useful to look at. This will, in fact, also have other references. Okay. Today, of course, we looked at Hawking's paper, which you can find easily. This statistical mechanics results are also, you'll find them in many places in the literature. Again, you'll find the references to them in this review. Okay, I'm sorry, I'm having a tech problem, so I can't see the chat anymore. So if you have a question, you're going to have to read it out. Or maybe I can see it. Now I can see it. I found a way to see the chat. Yeah, go on, please. Yeah.
Yeah, even the way you define the principle of ignorance, suppose even I am able to find only 1 degree of freedom more. Even Hawking himself find out using software problem, which means in his software paper. So it should solve this problem, isn't it? Just because of 1 freedom.
Oh, well, okay. So sorry, I didn't understand. What's the question?
Question is the way you define principle of ignorance based on.
I didn't define the way Hawking defined you.
Yeah, the way Hawking defined, yes, the 3 means based on no-hair theorem. Even if suppose I am able to find only 1 more degrees of freedom, that Hawking himself find in his software paper.
No, that would not resolve the issue, of course, if you could find 1 more degree of freedom. You see, unless you could find all degrees of freedom, it would just replace it with a slightly different principle of ignorance. I mean, let's say I had a theory in the world where there was 1 more long-range charge, right? That would not change this result. It would tell you instead of 3 pieces of data, you have 4 pieces of data. But of course, the initial state could have many more pieces of data. So, what was critical about this was not that there are 3 numbers you can read. If there were 10 numbers you could read off, there would still be a principle of ignorance. It would say you would have to trace over the inside subject to these 10 numbers. Okay. So the fact that it's 3 or 10 or 4 is not important. The fact is that what Hawking was saying was you don't have access to most of the data inside. You have access to only these finite number of degrees of freedom. As we will see next time, that's not true in a theory of gravity. But that was the principle of ignorance. The fact that if you find 1 more, it will not change it. It will just give you another principle of ignorance.
Yeah.
Yeah, can I ask? So to be clear that it's understood, this second argument is more robust because we get that the Hilbert space, each one got factorized in H2 and H3 times H3. And they say that we trace over H2 and automatically we get after this trace we get a mixed state, right?
Correct.
So that's it. That which is the paradox.
That's right. Exactly.
Okay. And other question is like it is true that factorization means maybe I don't know, maybe next time we'll see, but factorization means that you don't have any kind of interaction. Factorization happen when there is no interaction.
No. So factorization is actually you don't actually need factorization to have to trace. what you actually need in formal property is what's called the split property. You see, there's a subtlety about factorization. If you open Wald's book, he'll tell you Hilbert space of Mink doesn't factorize even in Minkowski space. That's because you have short-range interactions across the interface. Really, the kind of factorization we want to talk about is factorization where you have region R, then you make a collar region epsilon, and then you look at R bar. And all you want to say is that the R bar doesn't have any data about R, and you can specify data independently on R bar and R. But notice I introduced this collar region epsilon here. This is not strictly factorization. It's a weaker version of factorization. It's called the split property. And that's something that's explained in this paper. So what we actually need, Hawking's, it's like, Hawking's argument would also work if the split property was true in gravity. So one shouldn't get confused in details of factorization, which is subtle also in quantum field theory in the continuum limit. The split property is true in the presence of interactions. It doesn't require non-interacting theories. It's true also in the continuum limit. It just requires the existence of local operators in two regions which commute with each other.
Okay.
So there's no assumption that the theory is non-interacting. The split property is in fact true in all quantum field theories, but as we'll see, it's not true in a theory of gravity. Do you need to know UV complete theory of gravity to demonstrate the Hilbert space doesn't factorize? No, you don't. It's something that you can see already from the basic properties of gravity. Of course, you have to extrapolate. You have to argue that you have to have a system in which the whole discussion makes sense. So to that extent, you need a UV complete theory of gravity. But this is already clear if you carefully think of the constraints of low energy gravity.
Thank you.
I saw there were more questions about, I missed these questions because I was not seeing the chat. What about the distinguishing quantum states for same? This was maybe much earlier. It gives the largest probability difference for some measurement outcome in terms of trace distance. Just to say once more, there's a question much earlier, which I now see I missed. You can always find one observable that's different. If you give me one state, a pure state, I can always find one observable for which that pure state gives me a different answer compared to a mixed state. You give me a different pure state, I can find a different observable. What is that observable? For instance, the projector onto the state itself is one observable. It gives you one for a pure state and would give you something which is 1 by e to the minus s for the mixed state. So there's always some observable that given a pure state, I can find an observable that distinguishes between the pure state and the mixed state. That's not the point. I don't know the state. So what the question we're asking here is, you have an observable ahead of time, which Hawking computed, which was the number density, right? That observable is fixed. Now, given a typical pure state, how much do you expect that observable to differ between the pure state and the mixed state? The point is not, can you find some observable given a state which will give you a difference? Of course, there are some observables. So for any state, there's some observable for which that state is an atypical state. That's not in contradiction with the fact that if you fix your observable and give a typical state, you'll find an answer which is exponentially close to, the microcanonical state. Yeah. Also, one more question about why the Hilbert space is not factorized. That we'll see later. That we'll answer next lecture.
Sir, means Hawking quantum field theory is certainly right, and general relativity is also right. So where lies the problem? Why the Hawking calculations are wrong?
Well, we'll see that next time. So why don't we see next time? It'll take us too far afield. Right now, I just wanted to say what the Hawking calculation was. Right. So that's what the next 3 lectures are meant to discuss. I'm not going to answer your question, but I just don't want to answer it right now. That's what the course is about. So we'll see what's the mistake in Hawking's calculation. We'll see that in great detail. What's the mistake in Hawking's calculation? If the Hilbert space cannot be factorized, we cannot define density matrices and von Neumann entropies and black hole entropy. Actually, we can define the black hole entropy. The black hole entropy is a thermodynamic entropy. It doesn't require the Hilbert space to factorize. We can also define von Neumann entropies in an appropriate sense. But the black hole entropy is a very physical object. It has to do with the density of microstates. That can certainly be defined. Okay. What we can do for local density matrices outside and for Neumann entropy is that we'll discuss. But the partial answer to this is the black hole entropy is a thermodynamic entropy. It doesn't require factorization of the Hilbert space. It just requires us to count the number of states that look like the black hole. It's a statistical calculation.